Somewhere in this sentence, a photon hit a detector, and the universe had to make a decision. That's not a metaphor. That's the actual literal claim that mainstream quantum mechanics has been making since the 1920s, and mostly getting away with because nobody likes to look at it too closely. Something exists in two states at once, until you check. And the instant you check, one of the states just stops being true. Not, we discover which one was always true. Stops being true. The universe apparently waits for you to look and then commits. That should bother you more than it does. It bothered Einstein until the day he died. It bothered Schrödinger enough that he built a thought experiment specifically to make it sound as absurd out loud as it is on paper. A cat, a vial of poison, a radioactive atom, and a box you're not allowed to open. The cat is not probably alive. The cat is, according to the textbook version of quantum mechanics, alive and dead simultaneously, right up until observation forces a verdict. There's a fix for this. It's been sitting in the literature since 1957. It doesn't require faster-than-light signaling, doesn't require the universe to care whether you're looking, and doesn't require anything mystical about the act of measurement at all. It requires exactly one thing: giving up the idea that anything ever collapses. Instead, everything happens. All of it. Every outcome, every branch, every version of the story where the cat lives and the one where it doesn't, all of it occurring in full, in a universal wave function that never actually resolves into just one answer. You're reading this in one branch of that wave function right now. This episode is about what that actually means, what part of it is solid physics and what part of it is still, honestly, a fight. Start with what quantum mechanics actually says, stripped of the popular science varnish. A particle state is described by a wave function, a mathematical object that assigns a probability amplitude to every possible outcome of a measurement. Before you measure a particle's spin, it isn't secretly up or down with you just not knowing which. The equations describe it as genuinely, physically in a superposition of both, the way a wave can be a mix of two frequencies at once. This part isn't controversial. Every physics undergraduate learns it, every quantum computer built in the last decade depends on it working exactly as described, footnote 1, and no experiment has ever caught the math misbehaving. The controversy starts at the next step. The Schrödinger equation, the equation that governs how a quantum system evolves over time, is smooth, deterministic, and never produces a single definite outcome on its own. Left alone, it just keeps describing superpositions forever, growing more tangled as the system interacts with more of the world around it. But when you actually measure something, when a detector clicks, a cat lives or dies, a screen lights up in one spot instead of a blur, you get one answer. Not a superposition. The standard fix, formalized in the 1920s and still taught first in most classrooms, is called the Copenhagen interpretation, and its solution to this gap is to simply declare it a separate rule. Measurement causes collapse. The wave function, smoothly evolving one moment, snaps to a single value the next, governed by a completely different piece of math than everything else in the theory. Copenhagen doesn't explain what counts as a measurement, what physically causes the snap, or why the universe should behave by two different sets of rules depending on whether something is being watched. It just asserts that it does, calculates correctly, and moves on, which is exactly why it's remained the working default for a century. It's not that physicists believe collapse is well understood. It's that the equations work either way, so most of them shrugged and got back to calculating. Not all of them shrugged. And in 1957, a Princeton graduate student named Hugh Everett III wrote a doctoral thesis that took the shrug personally. Everett's move was almost insultingly simple. What if collapse just doesn't happen? What if the Schrödinger equation is the whole story all the way through the measurement, with no special extra rule bolted on at the end? Footnote 2. Here's what that actually means. When a quantum system interacts with a measuring device, a detector, a cat, a physicist checking a screen, the device doesn't force a choice. Instead, the device becomes entangled with the superposition itself. The detector that saw the particle spin up, and the detector that saw the particle spin down, both exist in full as two branches of one continuously evolving universal wave function. Nothing collapses. Everything that was possible before the measurement is still there after it, just no longer in a single, tidy overlap. It's split into separate, non-interacting threads, each one internally consistent, each one containing a version of the detector, the cat, and eventually the physicist, all convinced their branch is the only one that happened. This is where the popular parallel universes language comes from, and it's worth being precise about what it does and doesn't mean. There is one universal wave function, not a stack of separate universes bumping into each other, not a multiverse assembled from independent pieces. Physicist David Wallace, one of the leading contemporary defenders of the interpretation, describes the branches as emergent structures that appear within the wave function the way a wave pattern emerges on the surface of water, real and physically meaningful, but not separately created out of nothing at the moment of measurement. Footnote 3. The mechanism that makes a branch behave like a self-contained world rather than a smeared mess is called decoherence. As a quantum system entangles with more and more of its environment, the different branches lose the ability to interfere with each other, for entirely ordinary, well-understood physical reasons. Footnote 4. Decoherence has been directly measured in laboratory settings and is not, itself, controversial. It's one of the best-tested phenomena in modern physics. What decoherence explains is why the branches stop talking to each other. What it does not resolve is whether the other branches are still there, in any meaningful sense, once they've decohered, genuinely existing, unobserved versions of events, forever inaccessible to you but no less real for it. That's not a physics question anymore. That's a philosophy of physics question, and it's the one the field is still actually fighting about. Physicist Bryce DeWitt, who popularized Everett's work in the 1970s and coined the phrase, many worlds, described his own reaction to first taking the idea seriously as something closer to vertigo than satisfaction. The sense of literally splitting into copies with every quantum event, billions of times a second, none of which any single copy will ever experience. Footnote 5. This is where the episode has to be honest about the difference between the math and the metaphysics, because they're not the same fight, and conflating them is how most pop science coverage of this topic goes wrong. Solid, essentially uncontested physics. The Schrödinger equation, unitary evolution, and decoherence. Nobody serious argues these are wrong. Quantum computing, laser physics, and a significant fraction of modern electronics engineering assumes superposition is real and behaves exactly as the equations describe, and none of it would work if the underlying math were mistaken. Footnote 6. Everett's actual technical contribution, showing that collapse is not mathematically necessary to explain everything we observe, is also broadly accepted as a legitimate, internally consistent way of reading the equations. This isn't a fringe reinterpretation. Many worlds is one of the major, seriously debated interpretations of quantum mechanics in professional physics and philosophy of physics departments today, not a rejected curiosity. Genuinely open, still contested, two separate problems, and it's worth naming both specifically rather than blurring them into a vague, some scientists disagree. First, the ontological question. Does declining to add a collapse postulate actually commit you to the literal physical existence of every branch, or is that an interpretive leap beyond what the math requires? Philosopher of physics Adrian Kent has argued the existence of unobserved branches is doing more metaphysical work than the formalism actually earns, and that alternatives, Bohmian mechanics, which keeps particles definite at all times and guided by a hidden pilot wave, or objective collapse models like GRW, which propose a genuine, spontaneous, physically real collapse mechanism with its own testable parameters, remain live, competing ways to read the same equations without multiplying worlds at all. Footnote 7. Second and more technically serious, the Born rule problem. Standard quantum mechanics says the probability of an outcome is tied to the square of its amplitude. Some branches are more likely than others. But if every branch genuinely happens, in what sense is any outcome more probable than any other? Physicist David Deutsch and, later, David Wallace have proposed a decision-theoretic derivation, arguing that a rational agent inside a branching universe should still weight their expectations according to the Born rule even though every outcome occurs, treating the weighting as something closer to a rational betting strategy than a literal frequency. Footnote 8. Critics, including physicist Hugh Price, argue this derivation quietly smuggles in probability-like assumptions it's supposed to be deriving from scratch, that you can't get genuine uncertainty for free in a theory where nothing is actually uncertain. Footnote 9. As of the most recent published exchanges on the subject, this argument has not been resolved to the field's general satisfaction, and it's arguably many worlds' single largest unsolved technical problem. It is exceptionally fascinating that the mathematics does not disagree with itself on this point. Every branch of the calculation checks out cleanly every time. What remains unresolved is not the arithmetic. It's what the arithmetic is describing. That is, I would suggest, a more interesting kind of uncertainty than the ordinary kind. Set the interpretive fight aside for a moment and take the theory on its own terms. If it's right, then right now, this instant, there are, conservatively, given how many quantum events are happening in your body and your surroundings per second, an almost incomprehensible number of branching versions of you, each one experiencing a slightly, or wildly different continuation of this exact moment. This is where the track's through line lands its fourth application. The universe wasn't big enough, asked why the physical constants happen to permit observers at all, a level 2 question about which laws a universe needs. You don't need string theory, asked why an infinite ordinary universe would already guarantee endless repetition of every possible arrangement of matter, no exotic physics required, a level 1 question about space. The simulation hypothesis asked whether the substrate running the calculation even matters to the argument, whether observer selection reasoning survives being agnostic about what's underneath it. This episode's version is narrower still, and in some ways the strangest. It's not asking why a universe exists that permits you or why space is big enough to contain you, or what's running the calculation. It's asking why, given that every branch is equally real and equally populated with a version of you, your experience continuity happens to be tracking this one, this outcome, this history, this particular thread through the tree, rather than any of the others you also, in some sense, are. Nobody has a fully satisfying answer to that. It's not obviously a different question from the Born rule problem in section 3. Some philosophers of physics treat them as the same puzzle wearing two different hats. But it's worth stating on its own terms because it's the sharpest version yet of the theme this track keeps returning to. Every prior entry has asked some version of, given the full space of what could exist, why find yourself in the corner of it you actually occupy? Level 2 asked it about constants. Level 1 asked it about location in an unbounded space. This entry asks it about a branch in an unbounded tree of outcomes, all equally real, all equally populated, the same self-location question, applied to the least intuitive substrate yet. Here's where this theory earns its human precariousness footnote, and it's worth being unusually direct about it, because the internet has run away with a version of this idea that the physics does not support. It goes like this: if every possible outcome happens in some branch, then there's always a branch where you survive anything, any accident, any illness, any conceivable threat, no matter how astronomically unlikely that survival is in any single branch. Some early, informal discussions of many worlds, including from physicists who otherwise took the interpretation seriously, floated a thought experiment sometimes called quantum suicide, using this logic to argue that a repeated, sufficiently quantum random gamble with your own survival should, from the first-person perspective of the surviving branches, feel like immortality, because the only branches where you're around to notice are the ones where you kept surviving. This does not work as a real-world argument, and it's worth being plain about why, rather than leaving it as an intriguing unresolved puzzle. First, it depends entirely on the still unresolved Born rule question from section 3, on some genuinely contestable claim about how weight, or likelihood distributes across branches, not a settled result. Second, and far more importantly, it says nothing whatsoever about the branches where you don't survive, and does nothing to reduce the reality or the consequences of those outcomes for everyone connected to you inside them, for the people in those branches who do experience the loss. Some version of you lives was never the good news it's occasionally been dressed up as. It was always going to be true regardless, in exactly the branches where the people around you experience exactly the outcome you'd expect from taking a genuine risk. Treating it as license for anything is a misreading of the physics, not a clever application of it. The question is that I must go faster. Except, and stay with me here, faster assumes there's one of you experiencing it in one direction at one speed. Which, if this interpretation is correct, was never actually true. Somehow that fact has never once made anyone drive more carefully. None of this changes anything about tomorrow. That's worth saying plainly because a theory this strange has a way of making everything else feel smaller by comparison, and that's not actually the honest takeaway. If ever it was right, there's a version of you watching a completely different episode right now, maybe one that never got made on a channel that split off into some other tone entirely. There's no way to reach that version, no way to compare notes, no experiment that will ever tell any branch what any other branch is up to. Whatever's happening over there is, functionally, none of your business, And whatever's happening over here is the only version of your business you'll ever actually have. That's not a small thing. It's not a diminished thing either, just because it's one thread out of an incomprehensible number of them. It's a Tuesday. Somewhere, a slightly different version of that Tuesday is also happening, and it doesn't make this one count for any less. There's still a lot of universe left to look at. Turns out there might be a lot more of it, in directions nobody's built a way to check.